a brief overview, kind of review of what we did learn about graphene. Okay, so I'll do the first one with you, but basically I want you to review how you can, or what a graph should look like if it is zero order. If a reaction is zero order, what does its graph look like? What does its graph look like if it's first order? And what does its graph look like if it's second order? So we're going to label, this is just for the decomposition of ammonia. So ammonia is obviously my reactant. And we're going to label everything, the y-intercept and the slope. So for example, a zero order graph should look like this. Concentration of ammonia versus time. And then the y-intercept is initial concentration. Okay. And remember, it's a straight line if it's zero order, and the slope is minus k. So if a reaction is zero order, in general, this is what the graph would look like. So I would like you to please take a moment and review what would a first order graph look like and what would a second order graph look like. So this is what a first order graph should look like with natural logs of concentration versus time. And then again, the slope is minus k for first order still. But again, the natural logs end up being there because of calculus. That's their, it was a rate law rearranged using calculus and integrated, and that's where the natural logs came from. And then a second order graph is 1 over concentration with a positive k slope. So this is a second order graph right here. Any questions before we move on? All right, so the Arrhenius equation is no longer on the AP test. I'm going to do one little problem with you, and then we probably won't ever do it again. You might see one on your homework. I will not give this to you on a test, or it will not also be on the AP test, but I still want to kind of show it to you. So far what we've been doing is we've been looking at how concentration changes the rate. Sometimes it could speed it up, slow it down. Sometimes it has no effect. But let's look at this equation. Okay, this is the scientist. He's a Swedish scientist. Where we have the rate log constant k equals this frequency factor, which I don't need you to know this, and then this is your mathematical e to the exponent up here, where you have activation energy, the gas constant, which we'll talk about in a second, and temperature. So basically the whole point of this, and I have mentioned it to you before without showing you, is that the rate law constant depends on temperature. So changing the concentration does not change the rate law constant. It might change the rate, but it doesn't change the constant. But temperature will actually change. Changing the temperature will actually change the constant. Okay? Now, what they did is they took this equation right here and they got rid of the E function by taking the natural log of both sides. Now, I don't need you to know how to do that, but just know that this is just a manipulation This is just a manipulation of this where they did the natural log so they can bring that exponent down. Okay, now the reason that this came about is because, oh look, this looks like a straight line. Again, the equation for a straight line. And the reason why sometimes this was asked in the past is because they sometimes asked you for the activation energy of the reaction. And you go, well, how would I do that? Well, if you have data and a graph, and we have this equation that they used to give you, so this used to be on your equation sheet, so y equals mx plus b. So you'll notice your x-axis right here is 1 over t, okay? And then the thing is you could see that this thing is slope. So if you could figure out the slope with data points and we could look up the gas constant, you could determine the activation energy of the reaction using this graph right here. So we are going to do one bit of practice with it where we are going to find the activation of the energy of this reaction given this graph. So we go, okay, slope equals minus EA over R, correct? Well, if I want to find activation energy, I just multiply R by both sides. And then I move my negative sign over. Okay? So it's minus R times the slope. Well, what slope? Y2 minus Y1 over X2 minus X1 is my activation energy. So R is your gas law constant. And you go, okay, so you go to your equation sheet. Okay, and your gases are on the second page. And you see a handful of gas law constants. And you go, well, how do I know which one to use? Well, activation energy, you're probably going to want a unit that mentions energy in it. And so that's going to be our first one because that first one has the joule unit in it, and joule is a unit for energy. So we're going to pick this R constant to use, the 8.314 joule per mole Kelvin. So it's minus 8.314 joule per mole Kelvin times, and then now we're just going to use our data points, y2 minus y1 over x2 minus x1. So go back to the graph. Y2, it's hard to see on here, so I'll try to go here and see if this helps. Y2 is negative 0.5 and Y1 is negative 1. So I'm not negative 0.5, negative 5, excuse me. So we've got negative 5 minus negative 1. In essence, that's negative 4, right? Divided by x2 minus x1. Well, x2 is 3.8 and x1, so x2 is 3.8 and x1 is 3.4. So 3.8 minus 3.4 is 0.4. Now, this negative and this negative are going to cancel. And 0.4 divided by, 4 divided by 0.4 is 10. So 8.314, and then, oh, sorry, I forgot to point out. Notice that the units on the x-axis are K minus 1, which is what gets rid of our Kelvin. So the answer is going to be in joules per mole. So it's 83.14 joules per mole for the activation energy. This is how much energy you have to put in to start the reaction. Okay. So that's basically it for the Arrhenius equation. Again, you're not going to see it on the AP test or my test, but I just did want to show you what, like, kind of what they used it for. And again, it proved that the rate law constant changes with temperature. Okay, so this last thing that we're going to do is Beer's law. So let's flash back and remember what Beer's law is. Beer's law is A equals ABC, and Beer's law is used for things that have color. You can measure the absorbance based on how much light is being absorbed for things that are colored. It does not work for colorless solutions. So A stood for absorbance. Little a was the molar absorptivity constant that's specific to the substance you're looking at. B is the path length, which is just the size of your test tube or your cuvette. So like if you have this container that has your solution in it, the path length is just how far the light is traveling through the container, okay, with your solution, all right? And C is the concentration of the solution. As you see, absorbance and concentration are directly proportional. Low concentration, low absorbance, high concentration, high absorbance. Okay? So we're going to use Beer's law and mix it with kinetics, with rate laws. So you go, well, how would you do that? Well, look at this fake reaction. So they do 3 different experiments. So experiment 1, experiment 2, experiment 3, okay? Where they have known initial concentrations of each of your reactants, okay? And they measure the absorbance versus time. And you go, oh, well, what is that going to give us? Well, if you know absorbance, you should be able to find concentration at any given moment if you have enough of the pieces using Beer's law. So look at this reaction. You have some substance B that's colorless reacting with some substance C that's green, meaning your initial solution is green, because if something's colorless and something's green, it's going to look green. Now, the reason you can measure the speed of the reaction with Beer's law and absorbance is because if you look at your products, they're both colorless, meaning the green is disappearing over time. So if you can look at the change in absorbance over time, you can end up finding the change in concentration over time by the method of what are called initial rates. So look at initial concentration, and then they switch it up, and then they switch it up. So remember what that looked like a long time ago. Oops, I want to show you. Is this, right? Here's my first initial concentrations for experiment 1. I just plugged them into the data table, right? It's 0.1 and 0.1. For experiment 2, it's 0.1 and 0.2. So look, experiment 2, it's 0.1 and 0.2. Experiment 3, it's 0.2 and 0.1. So if we can figure out the rates, we can use this data table to figure out a rate law, okay? The first thing we have to do, though, is find the little baby A of the colored reactant. Remember, we're always going to focus on the colored reactant for Beer's law because a colorless reactant tells us nothing using absorbance. No light should be absorbed in a truly colorless or transparent solution. So how do you find little baby A? Well, you use Beer's law, A equals ABC. You rearrange it to solve for little baby A. So A divided by BC is little baby A. And then you pick any data point where you know the concentration of your colored reactant. And your colored reactant is reactant C. Well, you should know your initial concentration for each one of these 3. So it doesn't matter which one you use, but you're just going to pick one. Because if A equals A over BC, and I know B, it's right here. It's a 1 centimeter cuvette. That just means container or test tube. If I know the absorbance and I know the concentration and I know B, I can find A. So in second period, I did experiment 2, and in third period, I did experiment 1. So now that it's fourth period, I'm going to do the third experiment. I'm going to use this one. I know my concentration is 0.1 molar initially. Well, initially means time 0, right? So the absorbance at time 0 is 0.5, right? 0.5 is my absorbance at time 0. So A is 0.5 divided by, the path length is 1 centimeter. So it's 0.5 divided by 0.1 and times 1. Well, 0.5 divided by 0.1 is 5. Now notice that centimeters and molarities are in the bottom. So the answer is 5. Little baby a is 5.0 m minus 1 because it's in the bottom, and centimeters minus 1 because it's in the bottom. As long as we're using the green substance in the reaction, this will not change. An example of a substance that's green in solution is like nickel 2 plus ions. So maybe this is the constant for nickel 2 plus ions. If the substance were not green, let's say it were blue, this would not be the constant. The molar absorptivity constant changes based on the identity of the chemical we're looking at. But if, as long as we're doing the same reaction where B plus C is making D and E, this will always be our little baby a that we can use for the math. So we have a, little baby a now. It will always be this number. Okay, so now we go, well, okay, I have little baby a. How can I find the rate? So you go, well, what is rate? Well, rate is change in concentration over change in time. Now, I'm going to change this. Oops. I know I have A as generic, but it really should be for C, right? Because that's the experiment we're doing. It's substance C, okay? And why don't we use B? Why aren't we finding the rate of B? Well, B is colorless. So you're not, the absorbance in this experiment is coming from your colored species, not from your colorless species. So that's why we're saying that the thing that's green is the thing that we're measuring. So remember, change in concentration over change in time is some, it doesn't have to be final, but some value for C minus your initial concentration for C. Well, if you go back here, every single experiment, you know initial concentrations. They're given. So what's missing? What's missing is the concentration at any other time. So like I have absorbance at 60 seconds, and I have absorbance at 120 seconds, and I have absorbance at 180, and so forth, but I don't have concentrations. So I need to find a concentration, another concentration at any given moment. So for the method of initial rates, I need to get the rate for experiment 1. So what am I going to do? Well, to find the rate, I need to do change in concentration over change in time. Well, I'm missing this. So what I'm going to do is I'm going to find the concentration at any given point using Beer's law, right? A equals ABC. So A over AB is C. You can use this to find the concentration at any given point as long as you know all 3 of these numbers. So we're going to use our graph. So let's look at experiment 1. Let's do, this point is, you're kind of like guessing, right? Because it's in between numbers. So let's do this point right here. Doesn't this look like 0.250 and 120 seconds? It does to me. So 0.250 absorbance the absorbance is 0.250 at this point. The molar absorptivity constant we just solved for, it was 5 m minus 1 centimeters minus 1, right? And the path length is given in the problem. It's 1 centimeter. So 0.25 divided by, 0.25 divided by 5. So we get the concentration is 0.05 molar. So this absorbance right here corresponds to a concentration of 0.05 molar. So look, my initial concentration with an absorbance of 0.5 was 0.1 molar. So my concentration has dropped over time down to 0.05 molar. So after 120 seconds, the concentration has dropped to 0.05 molar. Okay, well now I can find the rate then. So the rate is change in concentration over change in time. Now remember, reactants lose concentration, so you have to throw your negative out there. So it's minus, we're doing the concentration at this point, 0.05 minus initial concentration, 0.1 of substance C. So that's my change in concentration over change in time. Well, 0 to 120. What's that difference? 120 seconds. This is molarity. So what is this rate? So you take 0.05, you subtract 0.1, but remember there's a negative out front, so then you'll take the opposite. So divide by 120, and you get, it's like 4.16 something, right? So again, this is everything I just said. Okay, 4.2 times 10 to the negative fourth molarity per second. That's the concentration, or that's the initial rate for experiment 1. So now we have to do this again for experiment 2, and now we have to do this again for experiment 3. So experiment 2, that's this middle graph, right? Okay, I know the initial concentration of C, right? I need to find the rate. What is the rate? Rate is change in concentration of C over change in time. This is what I need to find. And you go, okay, minus, I don't know any other concentration but my initial one. So I need some concentration minus my initial is 0.2 over change in time, right? So I'm like, okay, I'll find the concentration at a different point on here. Here's my initial one that corresponds to that concentration, but I don't know this guy or this guy or this guy. I do know its absorbance, but I don't know its concentration. So pick a point that like looks like a good, nice number. So like, look at, this is like 0.750, right? These look pretty lined up. So an absorbance, if you know absorbance and you know little a and little b, you can find concentration. So what's the absorbance? My absorbance is 0.750. What's my constant? We did that a long time ago. 5 n minus 1 centimeters minus 1. What's b? It's 1 centimeter. So 0.75 divided by 5. And I get 0.15. So what does that mean? That means 0.15 molar is this data point right here. So it was 0.2 molar. After 60 seconds, it's dropped to 0.15 molar. So 0.15 molar, change in concentration over change in time, 60 seconds. Okay, so what do you get? You get, oops, 8.3 times 10 to the negative fourth molarity per second-ish. Okay, do it again one more time, but for the third experiment. So again, I need to find the rate. What does rate mean? Rate means change in concentration over change in time. Right now, the only concentration I have is initial. I need any other concentration at any other moment. So let's see, what lines up really good on here? So my third experiment, right, this is what I'm doing this one. So it looks like this is a pretty good point, right? 0.25 in 60 seconds. So I need to find this concentration right here. I have its absorbance, but I want its concentration. How do I do that? I rearrange Beer's law. A equals ABC. Rearrange. Absorbance for this point right here is 0.250. Molar absorptivity constant, little a, is 5.0. M minus 1, centimeters minus 1. Path length is 1 centimeter. Centimeters cancel. So at this point right here, the concentration has dropped to 0.05 molar. So initial concentration is 0.1 molar, and after 60 seconds, it's dropped to 0.05 molar. So how do I find the rate? Don't forget the negative out here. So negative 0.05 minus 0.1. This one minus this one, change in concentration, over change in time is 60 seconds again. And we get same number, huh? Okay. Now, yes, this only works for colored species, and to be honest, it's really usually just aqueous solutions, no solids. It could work for gases as well, but it's mostly aqueous solutions for the most part. So now look, this is like what we're used to doing for finding rate laws. So your job is to find a rate law. Well, what do rate laws look like? Well, they look like this. So we have reactant B and reactant C, and we want to know what orders they are. So let's look at our chart. Look at. So while B is staying constant, C is doubling in concentration, and the rate is also coming close to doubling in concentration. So what does that look like? So the rate is doubling. The concentration of C is doubling. So what's this power right here? 2 to the what is 2? 1. So it's first order with respect to X. I'm sorry, with respect to C. Okay, now let's find B. Well, it would be helpful for B if C was not changing, right? That could help us. So let's see. Let's find an experiment where C is not changing. So that looks like 1 and 3 is where C is remaining constant. So from 1 to 3, B is doubling. The concentration of B is doubling, and the rate is also doubling or coming close to doubling. So if the rate is doubling and the concentration of B is doubling, 2 to the what power is 2? 1. So it's 1 again. So it's first order with respect to B and first order with respect to C. So there's my rate law. Rate equals K, the concentration of B, times the concentration of C. And then now they want you to find the rate law constant K. So now you have to pick any experiment you want and plug and chug the numbers in. So let's just use experiment 1. 0.1, 0.1, 4.2 times 10 to the negative 4th. So rate, I just rearranged first before I plug the numbers in. Right, this is just algebra where the B and C come on the other side. Rate is 4.2 times 10 to the negative 4th molarity per second divided by 0.1 molar divided by 0.1 molar. Molarity cancels. We're left with 1 molarity in the bottom and another seconds in the bottom. These are both in the bottom. So you get 0.042. M minus 1, S minus 1 is my rate law constant K. All right. So I'm going to stop here. I am going to actually record the next little part that you can watch on your own, but I am going to stop here. You guys can head out. So these practice MCQs, I'm going to just go over really quickly with you. So they're just taking a reaction, A, B, going to C. A is blue, B is colorless. So obviously the solution is blue, and then it's turning into yellow. They tell you that the reaction is zero order with respect to B. That means changing B's concentration should not have any change on the rate or the speed of the reaction. And they tell you how much they add of each substance. They mix them, and then they put it in the spectrophotometer and basically just shoot light through it to watch as it changes color from blue to yellow as the reaction progresses. So you can see like the absorbance is decreasing over time because the concentration of A is decreasing over time. It says approximately how much time was needed for 75% of the initial amount to react. When you see something like this, 75%, I need your brain to think half-life because, right, after one half-life, right, so you have like A, and then you have half of A left, right? So this is like 50%. And then it decreases in half again, right? So you'd be at 75% reacted, which is 25% left, right? So if you start off with an absorbance of 0.8, which is directly proportional to concentration, look at how long it took to decrease in half. Absorbance and concentration are a direct proportion. So it took 30 seconds for it to decrease in half. So you have half left. And then it decreased in half again in another 30 seconds. So this is the perfect pattern for half-life. So this is 50% left. This is 25% left, which means 75% reacted. So the answer is 60 seconds. It took 60 seconds for 75% of it to react, also known as 25% of it being left. Okay? I'm going to skip this one, but what is the order of the reaction with respect to A? Well, what do we say half-life is? In this class, half-life is first order. So first order kinetics is how half-life is determined in this class. So the answer is first order because this is showing you the pattern of half-life. Okay?